Okay, good morning. Welcome to
FamilyMath number 961.
FamilyMath 961. So today we're doing problem number 5 from Steller's 50 Challenging Problems in Probability. It's this problem right here. It says, in connection with a carnival game, a player tosses a penny from a distance of about 5 feet onto the surface of a table ruled in 1-inch squares. If the penny, which is 3/4 of an inch in diameter, falls entirely inside the square, the player receives 5 cents but does not get the penny back. Otherwise, he loses his penny. If the penny lands on the table, what is his chance to win? Alright.
So I guess
I gotta remember to zoom out, because sometimes I forget that, so let's zoom out. Okay. Let's talk about this problem. What are some initial thoughts you have?
well, we might be able to draw out a graph and see out of the total area of the table what areas can he win on, because I assume it's just a random area that he lands on. So if he lands on an edge of a square, he loses.
All right, go ahead and draw whatever you think would be helpful to draw here.
So we have a table, and then we divide it into 1-inch squares.
Now the coins that I prepared for this are a little bit bigger than pennies, so we probably want to make sure that. So you probably want your grids to be a little bit bigger than that.
And then if the pennies, they're
Did you go get some pennies?
3/4 of an inch, and then there's going to be a certain area in here in each of the squares where he can actually win. And then if we even if we just find in one of the squares what's the area he can win, that's the probability that he wins, because the pattern is just repeated.
Okay. Oh, that's a great explanation. So what is solving this problem boil down to?
I think it's just geometry problem.
Okay, so now that your brother's back, would you explain kind of what your plan is? Thanks.
So we've got our pennies, and if we boil it down to just one of these 1-inch squares, and we can look at the total area in which this player can actually win.
Okay.
In one of the squares. And we find that as a ratio, and then that's going to be the probability.
Does that make sense?
Yeah, and you just scale it up for however many squares you have, and its probability stays the same.
Okay. Can you show a losing position?
Yeah, it would be something like this.
All right. Can you show one?
Or even that's losing.
Okay.
Yeah.
And how about a winning position?
And winning would be that's a win.
Okay. Nice. All right. So you ready to try to tackle this?
All right.
All right. Let's do it.